next speaker is David Poeppel. He is professor of psychology and neuroscience at the New York University. He has been a fellow at the American Academy. He has received the Daimler Chrysler Berlin Prize, and he has several other honors. He is a fellow of the American Association for the Advancement of Science.
Thank you.
David seeks to understand the basis of human speech perception, and there are several questions that motivate the research in his lab, including how vibrations in the ear, for example, sounds and speech, translate into abstractions in the head in the form of words, in the form of ideas. What are the temporal mechanisms that encode information on the auditory cortex, and how multisensory information is integrated in the brain, for example, in the context of audiovisual speech. And it's good to know that MEG has a very prominent role in his research, so we're looking forward to hear his talk. The title of his talk is Unpacking the Temporal Structure of Speech and Language Processing. David?
Hi there. This is your chance to update your Facebook status. So I'd like to thank the organizers for putting on this terrific workshop and for inviting me. I'd like to unthank the organizers for putting me after the fireworks of these three speakers and making me the last thing after that display of data and showmanship and lunch. So I apologize in advance, and I'll do the best I can to keep you alive, awake, and up to nourishment. So it's especially emotionally satisfying for me to be here because I'm an alum of this department. I got my PhD here. I was an undergraduate at MIT. So as an alum, it's satisfying to see what's going on because when I was a student about 20 years ago, the situation was a little different. So the overall structure of the problem has remained. You see one of my thesis advisors, Ken Wexler, extracting data. But it means that there's a sense of historical continuity of what we do, which is kind of satisfying. And the question we have to ask ourselves this morning is, are we doing any better? And we hope so. So Pat actually raised a lot of the functional anatomy of speech perception and language processing. And typically when we think about these areas, we think about them in spatial terms. So we try to make maps of things. That's what we get from the techniques we're most seduced by, right? So we're all in love with fMRI because we love the maps we make, and I have a horse in that race as well. So, here's a typical map of the functional anatomy of speech sound processing. It's also called the right view. And what it summarizes is that there are, very much in line with some of the anatomic data that Pat showed, that there is a series of boxes, you might call them corresponding to areas, that have the responsibility for mediating some kind of computation, which forms the basis of this. And there are pathways. So there's a pathway that's called, more or less a dorsal stream, more or less of a ventral stream, and all of these areas are connected in a sort of complicated way to provide what's actually possible. These kind of models, you don't have to take, you don't have to like mine. You can like someone else's. David Gao, who's sitting right there, actually has an interesting hypothesis about how you have more than one mental lexicon distributed across a ventral and a dorsal stream. So these are kind of live ideas. And lest you think that I only have one set of boxes, I have more boxes. So this isn't supposed to be a theory of everything. If you, jointly with Ellen Lau and Colin Phillips, we've developed a kind of functional anatomy of very simple aspects of semantics, in this case the semantics driven by single words. So why do I want to mention this to you? Because language is a complicated animal. And it's sort of time that we stop thinking about this at the granularity of entire domains of experience. So it makes very little sense from a theoretical point of view or a biological point of view to say, I study, words or syntax or something like that. It's computationally very rich and structured, and we have to start to get to a granularity of analysis that subdivides these into the right level of things. So that's where we're going to try to go. So when we do neurophysiology, what we're trying to do as an end game is to pick some boxes. I don't know, let's pick some here and try to figure out, well, what is actually the contribution of these to the calculation of what we're doing in your head? So I want to give you just 3 ideas, 3 very simple types of experiments that illustrate how I've been thinking about this and to really begin to get a grasp of what's going on. And I want to begin with something extremely simple. So the 3 ideas are something about timing, because that's why we're here at an MEG workshop. Something that has to do with what's a cognitive primitive. A long time ago, a few years ago, Nancy Canwisher, who's somewhere in the back, and I were sitting at some weird workshop, and we're trying to figure out, well, what's the sort of big picture issue we're trying to do? And the word, I think it was coined by Nancy maybe, it's really not a very attractive word. We're trying to find the human cognome, which is, I think that was your word. Wasn't the cognome your word? No, I like it actually. But so there's nothing. So I agree with the spirit of the cognome, but the word cognome is. But in effect, what we want to do is we want to come up with the parts list, right? So like a bunch of like engineers, we want to try to figure out what are the primitives, and I'm going to argue that there's a neural computational primitive that is roughly the syllable. And then I want to actually also, as mentioned by Pat, talk about internal forward models and analysis by synthesis. But let's start with something very gentle, a gentle, soft introduction, something everybody can enjoy, and we can do in the MEG lab during lunch, in fact. Namely, how lovely it is that the responses that we measure, for instance, to something really boring like just something like that, are precise, replicable, and incredibly sensitive to lovely features. So actually, Rita is the one who's done the foundational work on this for many years, and so I'm stealing from her playbook a little bit. So many of you know, maybe some of you maybe do not, that when you play some simple sound, so maybe this is just a tone, the most boring kind of experiment you can do in my lab, there's a cascade of responses. So, and there's a particularly big one that's about 100 milliseconds after the onset, and there's a bunch of others. So, in the best of all possible worlds, that's what you see when you see a response. And just to summarize how one might use this, in a recent paper from Professor Kakigi's lab, here's sort of a summary of the kind of things that you might see. So here's an on response. So there's nothing happening, then there's a brief tone, nothing, and a brief tone. And you see this cascade of responses, very characteristic, and you see how it changes as a function of the interstimulus interval. So that's nice. It's just a kind of reality check that your machine is working in some sense, right? So if you have a long break between onsets, you get a nice big long response. You also get nice responses to the offset. So if you have a tone on, and then there's a hole, and then on, and there's a hole, you see offset responses. Or you can have a change response. There's a sound, then there's a change. So let's say a kilohertz tone, then it changes, kilohertz tone, change, you get a change response. So that's extremely useful, and because it means it's always there. And if it's always there, then we can use it for something to test some hypotheses about something. Now, of course, the way these are typically done is the way we do it in the monkey research. That is, we stick somebody's head in the kind of toilet-shaped device, and then we record hundreds or thousands of trials. So people are sitting there, and they're going, beep, 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 or in Pat's case, ba, ba, pa. So there's some kind of cruelty to this. But it's useful because you get sort of high signal-to-noise data. And so let's, so far I'm enthusiastic, but I'm not yet really enthusiastic. I want to become really enthusiastic. So what do I do next? So let's do a slightly simpler, kind of what's the next big experiment you can do? The next dorky kind of thing. Well, let's just play people a tone of a different frequency, riveting. So it's beep, 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 this kind of thing. So it's less cruel, but still pretty cruel. So you're sitting there for a couple of hours, you're listening to different tones, and what you can see is that that big peak, that big response, which is like this, actually seems to vary systematically as a function of the frequency of the tone. That happens even when you adjust for loudness, so you play them at the same sensation level. So there's a very systematic relationship between the latency of the response and the frequency of the signal. So that's pretty cool. I mean, it's kind of boring, and you should be a little bit bored, but it'll get better. Trust me. So now, this kind of data you've gotten from repeating stimuli hundreds of times. So beep, 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 beep. Now, suppose you want, well, that's kind of cool, but I really want to know, well, how is something happening on the fly in the real world in a single trial? So suppose you do that experiment again, which I did with a bunch of colleagues from the Physikalisch-Technische Bundesanstalt in Berlin, which I'd like you to repeat now. Well, you can do that. Measuring now single trials. So is this response big enough, juicy enough, and reliable enough that in a single trial you can replicate that pattern of the relationship between frequency and latency? And you do. So here it is for the left hemisphere. Here it is for the right hemisphere. And to make it a little bit more, more useful or plastic for you, here it is for a bunch of participants to really show you that even in single trials, so this is a single exposure to a tone, that kind of timing information is extremely robust. So here's a list of participants. So there's 11 participants. And for each person, we separately calculate in the left and right hemispheres these peak responses in single trials. And then we estimate the latencies. And what you see is that you get a very systematic pattern for tones of different frequencies. So low-frequency tones give a longer latency than high-frequency tones. So you might think, well, where does that come from? Well, obviously it comes from the cochlea. Something like that is visible at the cochlea at a very small level, and it gets amplified in cortex. But it's very systematic for every participant, for each hemisphere, based on single trials. So now you might say, well, that's a little bit more useful, because now I can probably use that information to begin to get a sense of what might be encoded in an experiment, in a listening experiment. And just to sort of drive that home in a summary point, well, look, you can play, let's say, pure sine wave tones, a high one, a low one, and a high one, and then you can begin to play systematically different kinds of sounds and calibrate where other sounds might fall. So actually, Steve Stuffelbeam has participated in some experiments of this type, and over the years, we've figured out that you can actually, by looking at the timing of a response, give a lot of rich information about the identity and properties of the stimulus. So for instance, if you have something like an AM tone where you have a well-known spectral structure to the signal, you can actually figure out exactly as a function of its latency what it's going to be and what its mixture is and what its sidebands are. You can tell apart sine waves from sawtooth waves, square waves, and so on. Or, of course, you can start to work with speech sounds. For instance, ahs, which are fast, versus oos, which are slow, because of the details of their spectral structure. So forget all of these details. Who cares? Why am I telling you this? I'm telling you this because it's actually easy to understand conceptually, and it's useful because it lends credence to something important about neural coding, which is that something like a time of arrival code may actually be a very useful ingredient to give you information in terms of neural computation. So I'm not particularly, it's sort of an easy way to begin to make contact with a feature of systems neuroscience and computational neuroscience that you should care about. Namely, that is, in fact, what we really want to know, properties of neural coding. So this was sort of a simple introduction to how robust and sensitive these responses are. So now let's actually use them for something a little bit more sexy, I think. So now we're going to steal straight from the playbook of systems neuroscience. So a bunch of years ago, there were a couple of interesting experiments doing single unit recordings from the grasshopper and the zebrafinch. In the grasshopper case, they recorded, so grasshoppers have particular kinds of vocalizations that they make with their feet, so they're kind of footalizations. And the footalizations of a grasshopper or their song has some characteristics, and you can record from the grasshopper auditory neuron. You can record spike trains, and then the game they played in this nice paper from Andreas Herzen's lab is, well, look, if I have the spike train, can I collect information out of the spike train to classify what it is that I actually heard? Very nice. What they ended up doing was looking at the inter-spike train coherence from trial to trial for a given song. And then what they observed is that the information over a particular temporal unit was actually the identifier. You could use it as a classifier. A similar experiment was done in Kamal Sen's lab for birdsong. and zebra finch field L data. Same kind of idea. So this is kind of cool, right? So it means there's a lot of information in the single unit response to tell you something pretty rich about what you're hearing in terms of a conspecific vocalization. So we thought we should steal this or adapt it. So we did, and we stole it in the following way. We adopted and adapted it. This is work by a former graduate student, Huan Luo. Suppose that MEG signals are just like a big fat spike train, a lousy spike train, but nevertheless the same kind of deal. So what we tried to do is this. Let's play people where they're lying in the machine a bunch of different sentences, sentence 1, 2, and 3. And the game we play is this. Can we, from the recordings that we get from the MEG recordings, classify which thing they heard purely based on some property of the putative spike train or the MEG signal? So is there really rich structure in that? You understand the problem? So it's very, very straightforward. So now let me explain the analysis. And if you understand this, then the rest of this is sort of like falling off a truck. It's very straightforward. So the reasoning is this. It's exactly based on the single unit approach. You play a bunch of trials. So let's take sentence 1. You play sentence 1 a bunch of times. Let's say 20 times, 30 times, intermixed with other trials. You hear this, you hear that, you hear something else. And the goal we have is, suppose we look across trials now. We look at the response to a single trial event, but we want to know across trials, is there anything that's coherent in the inter-trial features of the data? So from here to here to here, what stays the same? Right? So there must be something that stays the same if it's really robustly encoding something about the signal. So the hypothesis is when we look, so the similarity of responses to this should be pretty high when compared to some control, where the control is some kind of mixture, which we call an across-group mixture of trials. So we have within-group data and across-group data. And the hypothesis is, look, the inter-trial coherence and power, or coherence and phase, should be bigger for this group, like a within group, than an across group. Does that make sense? That kind of is important, because otherwise it sort of becomes a real bummer. So you have to be like, yeah, this is awesome. Okay. Good, awesome, you're with me. So that's the experiment. So here we go. Let's see what happens. So participants listen to a bunch of these. So let's first level of analysis. Let's look at a particular channel. So this is a channel in the auditory cortex, which is independently defined by playing some beeps and boops. Here's the response to a sentence. Here's the control response to a bunch of different sentences, mixed. This is frequency. And this is now what we call this is a phase dissimilarity or a power dissimilarity. That is, we calculate the inter-trials, trial to trial, phase coherence and power coherence, and we then simply subtract the two. Now, one of these is not like the other, right? So there's a bump. And there's a bump that's not everywhere. There's a bump right here. There's a bump right here in the phase dissimilarity. So when you compare the phase here and the phase here, they're not the same. That's not true for power. So when you compare the pattern and power across these, you don't get anything interesting. And where is that bump? That bump is in the theta band. So this was out to 50 hertz, but the only real big bump is in the theta band. So it's the theta phase, the phase of the response in the theta band, that seems to distinguish between these different sentences. This is the same data for now a bunch of different channels independently analyzed. Now, when you look at the spatial distribution of this kind of phase response, you see that the theta response is pretty nicely organized, and the spatial topography looks like what an auditory response actually looks like. So it's pretty nice. Still with me so far? Okay. So the theta phase has the right sensitivity to discriminate between these different things. So what can we do next? Well, let's get a little bit more detailed about it. Let's say, if it really carries useful information, I want to be able to use that phase pattern as a classifier. So we take the theta phase pattern for a given sentence from, let's say, sentence 1, and we want to know, across the whole experiment, does the phase pattern to sentence 1 always get identified as sentence 1? And it actually does work that way. So take the original sentences. So you heard them just fine. Intelligibility was perfect. And we take the phase of that pattern, and sentence 1 gets classified as 1, 2 is 2, and 3 is 3. So far, so good. So it actually has the right specificity as well. So we're still pretty happy. Now we did a further manipulation. We took some materials that we adapted from a paper by Smith, Delgood, and Andy Oxenham, and we made some materials, some sentential materials, which were harder to understand. That is, we manipulated the psychophysical intelligibility for the participants. So now we know that for a normal sentence like this, you understand it just fine, right? So your intelligibility is essentially perfect. Then we did a bunch of acoustic manipulations to the stimulus to calibrate you into a certain level. So for instance, if you just bin it into four bands like this, your intelligibility goes down to about 85%. If you only play the fine structure, it goes down to something else. So we have a sort of sense of the individual score of people, right? So these sentences are in there as well. They're just the same kind of sentence, except you don't understand it as well in your behavioral report. So what do we do? Well, this is where it gets kind of cool. If you have the same data, if your intelligibility is systematically lower, the theta phase response is worse, and is worse as a classifier. So you don't have the same juice in that response anymore, and it gets worse as your intelligibility gets worse, right? So what does that mean so far? There's a tight relationship between your ability to decode the thing, to report an intelligible sentence, and the response in the theta band. So far, you still have to say yes. This is a yes response. But what is that supposed to mean? Well, this is what it could mean. Well, what is the theta band? Well, the theta band, as Pat just pointed out, is between 4 and 8 hertz. So that's a time period of roughly, let's say, ballpark 200 milliseconds. That's a reasonable period for the theta band. Well, what could that mean? Why does the phase pattern tell you something about the identity of an item? Well, suppose that what it reflects is a time window of about 200 milliseconds that slides across, and the phase of which is actually reset by something in the stimulus itself. So you have a 200 millisecond window that kind of goes across the stimulus and samples the auditory world, and the phase of that theta response is reset. That's why there's nothing in power, incidentally. Does this make any sense, or am I just making this stuff up as I go along? No, of course it makes sense. It makes deep, profound, important sense. And so here's a quick reason why it's not so bad. So take a bunch of sentences like this. So here's, we took many sentences. This is a recent work by Ilana Zion-Golumbich, who's a postdoc with Charlie Schroeder and me. So we take a bunch of sentences, we look at the envelope, we then calculate the spectrum of the envelope, and you see in the typical envelope, you see some peaks. The peaks are pretty low modulation frequency, and you see a huge bump at about 4 or 5 hertz. So there's something in the signal that has something about that time period built in. Still with me? So there's something actually in the physics of this. Okay, now we need some kind of linking hypothesis. That's all very nice and good. What does this mean about psycholinguistics? So there we have to turn to some pedantic, even German-style work from the Institut für Phonetik in München. So here you see actually just some characterizations, some descriptive characterizations of syllable duration across languages. Kind of interesting. So here's English. Here's a histogram of just duration of English syllables and Japanese syllables. Now notice, there's a big bump somewhere. That's good. Take here the jaw openings. This is old data from John Ohala. Or here's the very pedantic German study, histogram of syllable duration for German. So as you can see, this aligns pretty well. So there must be something very profound about that aspect of the input signal that you care about. So there's a tight link between syllable duration and the envelope and the thing we decode. So what's going on? Well, why was I excited about this? I was excited because it suggests that there's a very tight relationship between being able to parse a sentence into syllable-sized chunks and intelligibility. As if you're not able to actually break it into that size units, your perceptual performance is completely decayed. So I was pretty excited, and I said, yeah, I found something about an index, a neural index of intelligibility. I'm golden, we all have a party, I buy drinks, and in fact I did. So then, okay, we can do a little bit more. That was a kind of weird experiment. You know, you're hearing the sentences, you know, in an earphone. They're not very naturalistic. So we did another experiment. This is actually with Huan Lo and Sujiang Lu, who I think was a postdoc here with Bob Desimone, I believe. Who's now at the Chinese Academy of Sciences. And we did something a little bit more fun for the typical undergraduate. We played them the movie Dumb and Dumber, and which is a sort of cult film. And in this, so now it's a real audiovisual stimulus. So they listen to clips of Dumb and Dumber, and we do the same kind of analysis. I'm not going to go through too many details because it's a pretty gnarly experiment. But the question is, when you see an audiovisual movie, a much more naturalistic stimulus, do you get, and you calculate the inter-trial phase coherence both in auditory channels and in visual channels, do you get the same kind of overall pattern out? And I wouldn't be telling you this if it hadn't been true. You get a lovely pattern, and all the data, all the interesting action is in the low modulation frequency phase pattern and nothing so much in power. Still good, right? So I'm still pretty excited. So I still have something that really links intelligibility and some pretty obvious big neuronal response. Then, you know, you all know about reviewer number 3. But do you have postdoc number 3? So I have postdoc number 3 who says, well, you're a little optimistic. Let's look at this one more time. Because intelligibility, that's a sort of squishy notion. It's not very satisfying. There must be something about the physics of the stimulus. So Mary Howard did a very simple experiment. She said, let's do the same thing, just play the materials backwards. So, you know, no great shakes. You're lying there, you're listening to sentences, and you just, those you really don't understand. I mean, you can understand a little bit with a lot of practice. And here's the phase dissimilarity pattern we obtained for the canonical forward motion. So this is sort of a re-replication of the previous experiments. Here it is for the reverse. You're even better. So now I'm not so happy anymore. I mean, I didn't throw her out, but I was a little unhappy with postdoc number 3 because it really killed my buzz. And so that suggests that it must be something about the acoustics of the materials that are actually driving the response, right? So now I'm a little bummed. So what do I do next? So this is a story of the unraveling of an experiment. I only recommend this post-tenure, by the way. This is not, does not come recommended pre-tenure. So now we say, well, can we unpack this a little bit more to see, well, what's actually driving the response? If it's not, I thought it was intelligibility, I thought it was going to be rich and famous, and it didn't work out. So let's unpack this a little bit more. So we wanted to test, well, what aspect of the sound is contributing to this so we can understand it a bit better. So we make some new kind of sounds. We take a stimulus that retains the envelope. So speech has many attributes that you must analyze to understand it. Part of it is the envelope of the thing. Part of it is aspects of the fine structure. I'll come back to that in a bit. So let's make a stimulus which retains the envelope, but we fill it with some weird complex tone carrier, so you really don't understand it at all, right? So the fine structure of speech is gone. It's not like a classic Shannon stimulus. It's just a weirdly modulated signal, but it does have the original envelope. And I had all along claimed, well, what you do is you straight up lock to the envelope. We made another stimulus that just retains the fine structure. So you take the original signal, you decompose it into envelope and fine structure. You take the fine structure, and then you modulate it with a known signal. So for instance, let's take a 6 hertz amplitude modulation. So now you have original speech, fine structure, modulated with a known envelope, so you know what it should be, right? Now, what do we predict? Well, this stimulus that we made is not intelligible. So on my original theory, it shouldn't work. If we find this kind of pattern in our response, then the theta phase that I'm going on about reflects some kind of low-level characteristic rather than something lexical or intelligibility-driven. And that's the prediction. If we find this pattern, so now we take the fine structure stimulus that has a known analytic envelope, we should find this kind of pattern if it's really envelope following, because the envelope is the same on both the within and the across group comparison. So these are, from the envelope point of view, the same. We should be finding this pattern if it really is tracking, if theta phase is tracking the envelope as I had claimed and as people in Nina Krause's lab had claimed. And if we find this, we have to reject the hypothesis. So I wouldn't be telling you this if I didn't lose that game. So in fact, we find the pattern that supports a low-level analysis and one that rejects envelope following at the most straightforward way. So now I'm really having egg on my face, right? I'm really annoyed. So now we need the next hypothesis. What can we do to rescue this story? Well, what kind of hypothesis lends itself to that? I mean, what could actually be driving this kind of thing? Well, it could be that what you're really locking to is just discontinuities, some kind of edges in the material. So maybe what's going on is this is some form of edge detection in which you really need to build temporal primitives of the right granularity for psycholinguistic analysis is some kind of edge, literally like a visual edge, that permits you that kind of subsequent analysis. So we have edges. No matter what kind of stimulus you look at, you can sort of find discontinuities. So that's a possibility. I might say, look, maybe perception is just really about edge detection. Every time there's a transient, I say, oh, I care, I care, I care. Okay, that seems extremely undesirable, but it's possible. So how do we test that? So here comes the last in this experiment of unravelese. Then it gets good again, positive. Now this is pretty neat in its own right? So suppose we make an artificial stimulus where we put in edges of a known type. So here are a bunch of edges. So edges, we take, let's say, something like an FM sweep, like, and we make them of a particular temporal structure. So we draw them from a distribution that is either pretty short, intermediate, pretty long. So the long ones corresponding to theta band, more or less. The short ones corresponding to gamma band. And the intermediate ones corresponding to alpha band, more or less, squinting a little. And we concatenate things like that. And so it's a long, noisy stimulus that's full of edges, full of discontinuities. So now here comes the casus knaxus. If all you care about is any kind of discontinuity, and that's sort of the underlying infrastructure of perceptual analysis, then these things should behave the same way. There should be no principal difference. But if there are privileged scales, privileged temporal regimes, maybe in the gamma band, like you heard about from Pascal, maybe in the theta band, like I'm sort of trying to defend, then you should get some differential kind of thing. Now this really is cool and weird. Here's what you find. So here's now an intertrial phase coherence and power analysis, the same kind of flavor of analysis across different bands for these different stimuli. So let's just focus on this one up here. I mean, you can see there's nothing interesting happening in power that differentiates materials. There's nothing interesting happening in power coherence that differentiates the material. So let's look at the phase coherence again. So take the very fast stimulus that's modulated, so the stimulus is modulated in the gamma band, and look at its intertrial coherence in the gamma band. You get a lot of juice, but not so much in the other bands. Take the theta band stimulus. Very nice intertrial phase coherence when you look at the theta band, not so much in the others. The noise is flat. Now comes the really critical. What happens to the intermediate bunch of edges? They should also be there. They fall out. So the alpha band type of response doesn't actually give you the interesting pattern. That's pretty strange, because it's not like it's not there. It's a big bang against the system. But it means that not everything is in fact equal. You care differentially about things that are occurring in the statistics of things that are occurring on this time scale and on this time scale. What could that mean? Does that make any sense from an interpretation point of view? Well, yes. Actually, acoustic and articulatory phonetic phenomena occur on very different time scales. So one we just talked about, the speech envelope. Right? So this is about, let's say less than 16 hertz, mostly less than 10 hertz. But there's also, that's sort of typical, and I showed you at the beginning, peaks at about 5, 6 hertz. But there's also very rapid information, the typical time structure of which is much more related to gamma band phenomena. So let's say with 20 to 80 millisecond time constants. So that means you have primitive elements. So in terms of the parts lists, there are things in the parts list that are very fast and things that are parts lists that are very slow, but there's actually a hole in the middle. A similar thing is true for a bunch of non-speech perceptual phenomena. So there are many things that happen on the time scale of the gamma band and many things that happen on the time scale of the theta band, but there's a kind of non-overlapping discontinuity. So it looks like you're looking at the world on two different scales, or you're listening to the world on two discontinuous, non-overlapping time scales, which is pretty strange, right? So how do we account for that in the spirit of a proposal like the one that Pascal talked about earlier this morning? So here's a suggestion that Annelise Giraud and I have been flailing around with, trying to entertain. So what we really want, and this is actually building on experiments that we've done with Oded Gitza, who's here, and Charlie Schroeder. What we're trying to do is, well, look, the speech waveform looks something like this. And in the afferent pathway, the sort of spectral temporal encoding of this, you get a stimulus-driven spike train that's just constantly banging against you. And you need to structure it. Because you need to end up with, you need to go from some kind of continuous variation to some discretized package. So what do? Well, what we suggest that you do is you actually you capitalize on the intrinsic oscillations that the system makes available that happen on their own privileged time constants. So for instance, you have endogenous theta oscillations. These are very powerfully reset. Their phase is reset by bumps in the input. That, in turn, is actually nested with gamma oscillations that are both there. So there's actually, Pascal mentioned it, there's a very interesting systematic relationship between theta and gamma. The kind of conceptual consequence of which is that you end up with excitability cycles or packages of preferred interpretation of spikes. So you have you basically end up with packaging of information from a systems neuroscience point of view. Why do we care about that? Because we have to get away from what's purely there to what's purely there. Now, how we can make pretty precise predictions. We can say, look, for instance, if we recorded from layer 4, we would expect to see a transition from something like that's pretty much a continuous burst of spike trains to, let's say, output layers, let's say layers 1, 2, 3, you should get more this kind of organized spike train. So that's beginning to link speech input to firing at the spike train level at a granularity of analysis that I think is pretty provocative. I mean, it must be wrong, but I hope it's wrong in an interesting way. Okay, so what's the conclusion of this? So if the theta band is really that potent in driving you, you must do so. It's not necessarily directly the envelope. You basically set up windows that are scaled to the envelope. But it means that perceptually speaking, the syllable is a cognitive or psycholinguistic primitive, maybe a neural primitive in the sense of theta, and probably a computational primitive because it sets up how you do the subsequent calculations for intelligibility. And if these analyses are on the right track, there must be at least two primitive levels that are concurrent, that are ongoing at the same time. So you're viewing, it's not unlike the visual system, right? So V4 cells versus MT cells presumably sample the visual world not on the identical time scale. I mean, if V4 cells are a little bit more tonic and MT cells a little bit more phasic, you would get the same temporal discontinuity in how you view the thing. It's sort of borrowed from that. Okay. So this is purely based on MEG data. The entire thing is all MEG data of a very particular type, namely dealing with oscillatory structure of information and how it relates to particular manipulations. So let me give a last very quick examples of 3 or 4 minutes I think I have about the concept that was brought up by Pat, namely predictive models or analysis by synthesis. So this is a slightly different form of data. So first I showed you the sensitivity of auditory responses. Then I tried to show you the sensitivity of kind of exploiting the nature of oscillations to learn something about perceptual analysis. And now I want to show you a very kind of simple-minded canonical analysis of this, but that can inform us in interesting ways about a cognitive science model. So all of us are seduced by predictive models as sort of the currency, the flavor of the day, and you can see that from the input waveform to actually coming up with an acceptable word string in a syntactic sense, there's many places of sort of a bottom-up, top-down interaction. Actually, this functional anatomic model about semantics is actually dealing with, it's Ellen Lau's work dealing with the level of lexical analysis and syntactic analysis. But in speech comprehension, there's a lot of evidence for analysis by synthesis in the online construction. So there's a ton of evidence in perception. Now let me give you a very different kind of evidence from production. And this actually tries to link very directly to what's going on, for instance, in the birdsong model. So do I have 5 more minutes to do this? Finish it last? Yeah. Okay. I know you're dying to have lunch, as am I. So in production, very simple model. You want to say something, so that you have some kind of movement intention. You have a motor plan. You execute the motor plan. We have a hypothesis, since Helmholtz approximately, that there are a series of internal forward models or motor efference copies, slightly different from corollary discharge, closely related. So you have a forward model that estimates the motor state and one that estimates the sensory state. This is a large-scale hypothesis about prediction in cognitive science. How do you test this? Shin Tian, a postdoc in the lab, said, in most of these experiments, if you overtly produce, you have an overt movement and you have an overt perceptual thing, that's no good. So he decided to do this the following way. Adopting the experimental strategy of Steve Koslin of doing mental imagery experiments, he has people actually do mental imagery experiments of speech production. That is, he crosses out the overt output thing. Why is that useful? Because it could provide a direct test if this stuff actually exists. If you don't actually move your mouth and you don't hear anything, the question is, do you really see activation in the somatosensory system and in the auditory system that's a reflection of the prediction in precise ways? Because nothing was ever done. You didn't say anything. You didn't do anything. It had to be internally generated as a local prediction. So the way he tested this is to do an adaptation design. It's quite cool. So it's an MEG repetition priming or adaptation design. You hear a stimulus. If you hear it again, the second response should be lower. Right? That's, everybody thinks that. The interesting thing is, what if you imagine hearing it, and then you get an overt response? Or what if you imagine saying it, and then you get an overt response? If you imagine saying it, nothing ever happens. What will you find? Okay, so when you play an auditory stimulus, as I showed you at the beginning, you always get a canonical response pattern. Stop, red light. Here's what you find. So here's the typical repetition priming effect. So there's a response to the repeated stimulus, which is the red one. So that's reduced compared to a novel one. So when you hear beep, beep, you get reduction. What about imagining it? You also get response reduction, but it's a little bit later. But here's the cool part. Here's the exciting part. When you do either overt articulation or covert imagined articulation, you get actually a response enhancement. That is, now you get a repetition effect, but it's not just a one-size-fits-all thing. You actually get a priming. You get a featural priming of the enhancement at about 200 milliseconds. And you can see, using Mati's wonderful MNE software, how that works in the source domain as well. So what's the interpretation of this kind of thing? Well, this might suggest something like a dual-stream model of prediction. Namely, if the source of prediction, so prediction is always a top-down kind of thing. If the sources of prediction comes from ventral stream structures, so let's say from episodic memory retrieval, as in the Steve Koslin case, or lexical access, you might expect a response reduction. If the source of the prediction are dorsal stream structures, as in the articulation case, you might expect a response enhancement. It all converges on an abstract auditory representation. So you can use this kind of weird pairing of MEG repetition priming and mental imagery to test a pretty explicit hypothesis about how prediction is done in a kind of cognitive science context. I mean, this is one example of that. So I think that's pretty neat. So the 3 ideas I want to show you are that timing really does work and can be exploited to, at great detail in terms of hypothesis testing. That there's multi-time resolution processing, which I think is a triviality, but remains very controversial. I mean, somebody actually just took a really serious pot shot at me in TICS about this last week. And the ubiquity of forward models. For the very nerdy of you, for the neurophysiologically inclined, you should also be, so those of you who just live MATLAB all the time and can't sort of drag yourself away from it, you should be aware that there's now lots of cool ways to analyze these data. So if you're really a fan of reverse correlation or STRF-based analyses, There's now wonderful examples of how to use these approaches. Jonathan Simon and I Ding have done some elegant work showing this. If you're a different kind of nerd and you prefer a mutual information-based analysis of MEG data, that too can be accommodated even for the similar kind of thing. So there's now a range of toolboxes that permit the formulation of linking hypotheses between systems neuroscience approaches and these cognitive neuroscience data that we get, which I think is extremely promising for the next few years. So in conclusion, you should run, not walk to your nearest MEG scanner down the hall, because these kind of data, I think, stand to fulfill the promise of the MAR-type research program that was formulated here many years ago, namely that you have to have linking between a computational level, an algorithmic level, and an implementational level, and you can actually sort of cash out the promise of this by really focusing in a theoretically motivated way on the different boxes that you're trying to connect in the study of cognition and perception. Thanks very much.
Thank you, David. That was indeed a very entertaining talk. And I like the comment about running and not walking to the nearest MEG lab, I must say. We have time for one question from the audience.
In the visual system, what has been done is that flickering stimuli of different frequencies have been shown, and one sees that there's entrainment at a specific frequency. I think Christoph Hermann has done something like this, and he sees that there's some sort of resonance, steady state visual evoked potential. At gamma, I think at gamma there is one peak, and at alpha there in the visual system. I don't recall the details. Do you think your finding of intertrial coherence specifically for theta and gamma but not alpha kind of filtered thing is somewhat related to this?
Well, I mean, I want to take a stronger position on that. I want to say that there really are privileged timescales for this. That there's just intrinsically, as a function of the architecture of the system, that there are neural circuits that privilege gamma and privilege theta in a way that is not the same for alpha and beta. That just different operations are executed in those ranges. So I don't think it's actually filtered. I think it's reflecting a different type of computation that's being done there for that kind of thing.
But if you do, I mean you have done a spectral analysis of the envelope of your raw sound signals, and you find a peak in the theta range, 4 to 8 hertz. Do you ever, I mean, is there really a peak in the gamma range?
I mean, there's not a peak in the gamma range when you do it, but there is obviously tons of phonetic information carried there. Actually, the world expert on this is Oded Gitza, who's a very detailed computational model on how the interaction would be from the theta and the gamma range. The way, and I'm kind of adopting his position on this, which is what you use the theta for is to actually build units of the appropriate temporal granularity for parsing the signal. What the gamma would be reflecting is actually the decoding of the signal in a phonetic sense. So you have this kind of cascaded thing where you build the right units, and then you decode locally, and that would be in the gamma range. Now, you don't see so directly an acoustic correlate in the gamma range. It's a little bit more punctate, but certainly there in the sense that, you know, practically every burst in the onset of a consonant is something in that order. All of VOT is like that, more or less. I mean, there's FM sweeps are all in that sort of range in speech. So you can't ignore it because you have to decode it. I mean, you can't otherwise decode words. I mean, you can't live without it. That's the problem.
So let's thank David one more time.
So there's nothing. So I agree with the spirit of the cognome, but the word cognome is. But in effect, what we want to do is we want to come up with the parts list, right? So like a bunch of like engineers, we want to try to figure out what are the primitives, and I'm going to argue that there's a neural computational primitive that is roughly the syllable. And then I want to actually also, as mentioned by Pat, talk about internal forward models and analysis by synthesis. But let's start with something very gentle, a gentle, soft introduction, something everybody can enjoy, and we can do in the MEG lab during lunch, in fact. Namely, how lovely it is that the responses that we measure, for instance, to something really boring like just something like that, are precise, replicable, and incredibly sensitive to lovely features. So actually, Rita is the one who's done the foundational work on this for many years, and so I'm stealing from her playbook a little bit. So many of you know, maybe some of you maybe do not, that when you play some simple sound, so maybe this is just a tone, the most boring kind of experiment you can do in my lab, there's a cascade of responses. So, and there's a particularly big one that's about 100 milliseconds after the onset, and there's a bunch of others. So, in the best of all possible worlds, that's what you see when you see a response. And just to summarize how one might use this, in a recent paper from Professor Kakigi's lab, here's sort of a summary of the kind of things that you might see from the techniques we're most seduced by, right? So we're all in love with fMRI because we love the maps we make, and I have a horse in that race as well. So, here's a typical map of the functional anatomy of speech-sound processing. It's also called the right view. And what it summarizes is that there are, very much in line with some of the anatomic data that Pat showed, that there is a series of boxes, you might call them corresponding to areas, that have the responsibility for mediating some kind of computation, which forms the basis of this. And there are pathways. So there's a pathway that's called, more or less a dorsal stream, more or less of a ventral stream, and all of these areas are connected in a sort of complicated way to provide what's actually possible. These kind of models, you don't have to take, you don't have to like mine. You can like someone else's. David Gao, who's sitting right there, actually has an interesting hypothesis about how you have more than one mental lexicon distributed across a ventral and a dorsal stream. So these are kind of live ideas. And lest you think that I only have one set of boxes, I have more boxes. So this isn't supposed to be a theory of everything. If you, jointly with Ellen Lau and Colin Phillips, we've developed a kind of functional anatomy of very simple aspects of semantics, in this case the semantics driven by single words. So why do I want to mention this to you? Because language is a complicated animal. And it's sort of time that we stop thinking about this at the granularity of entire domains of experience. So it makes very little sense from a theoretical point of view or a biological point of view to say, I study, words or syntax or something like that. It's computationally very rich and structured, and we have to start to get to a granularity of analysis that subdivides these into the right level of things. So that's where we're going to try to go. So when we do neurophysiology, what we're trying to do as an end game is to pick some boxes. I don't know, let's pick some here and try to figure out, well, what is actually the contribution of these to the calculation of what we're doing in your head? So I want to give you just 3 ideas, 3 very simple types of experiments that illustrate how I've been thinking about this and to really begin to get a grasp of what's going on. And I want to begin with something extremely simple. So the 3 ideas are something about timing, because that's why we're here at an MEG workshop. Something that has to do with what's a cognitive primitive. A long time ago, a few years ago, Nancy Canwisher, who's somewhere in the back, and I were sitting at some weird workshop, and we're trying to figure out, well, what's the sort of big picture issue we're trying to do? And the word, I think it was coined by Nancy maybe, it's really not a very attractive word. We're trying to find the human cognome, which is, I think that was your word. Wasn't the cognome your word? No, I like it actually, but for putting me after the fireworks of these 3 speakers and making me the last thing after that display of data and showmanship and lunch. So I apologize in advance, and I'll do the best I can to keep you alive, awake, and up to nourishment. So it's especially emotionally satisfying for me to be here because I'm an alum of this department. I got my PhD here. I was an undergraduate at MIT. So as an alum, it's satisfying to see what's going on, because when I was a student about 20 years ago, the situation was a little different. So the overall structure of the problem has remained. You see one of my thesis advisors, Ken Wexler, extracting data. But it means that there's a sense of historical continuity of what we do, which is kind of satisfying. And the question we have to ask ourselves this morning is, are we doing any better? And we hope so. So Pat actually raised a lot of the functional anatomy of speech perception and language processing. And typically when we think about these areas, we think about them in spatial terms. So we try to make maps of things. That's what we get.
Our next speaker is David Poeppel. He's professor of psychology and neuroscience at the New York University. He has been a fellow at the American Academy. He has received the Daimler Chrysler Berlin Prize, and he has several other honors. He is a fellow of the American Association for the Advancement of Science.
Thank you.
David seeks to understand the basis of human speech perception, and there are several questions that motivate the research in his lab, including how vibrations in the ear, for example, sounds and speech, translate into abstractions in the head in the form of words, in the form of ideas. What are the temporal mechanisms that encode information on the auditory cortex, and how multisensory information is integrated in the brain, for example, in the context of audiovisual speech. And it's good to know that MEG has a very prominent role in his research, so we're looking forward to hear his talk. The title of his talk is Unpacking the Temporal Structure of Speech and Language Processing. David?
Hi there. This is your chance to update your Facebook status. So I'd like to thank the organizers for putting on this terrific workshop and for inviting me. I'd like to unthank the organizers